Alright, so I'm recording this as a little part 2 to my day 21, mostly just as an explanation, but some little side notes. I figured out a nice little way of optimizing this thing because I realized like you could just basically do a BFS and store the parity of each point you reach. So for example, when I reach this point, it's an odd parity because I would take even step, odd step. And then this point would be like an even step, odd step. This would be an odd step. This one would be an even step, so forth. And I just need to save those. And so because you do that, you don't need to recompute basically all of the points you've seen already. And so by making this a BFS, my code ends up running drastically faster. I currently, like, if I get rid of my code to render stuff, it runs in like half a second, which is nice. But so other than that, I added in some code to render using matplotlib, and I wanted to kind of explain a little bit more on the intuition behind actually the like the whole kind of pattern. So first of all, if you look at your input, something like to note is based on your S, here's your S, you end up having complete clear horizontal lines and completely clear vertical lines also. And also, if you squint your eyes a little bit, do you see how there's a little diamond shape kind of coming out here? This ends up giving us some nice little symmetry patterns. But basically, if you still end up and you're looking at this and you're like, this is not really, like, I don't really know where to go. My code is going to take a couple years to run. I'd recommend kind of going ahead and making a visualization. So what I did is I kind of did that too. So here, I just visualized the grid. This is better. All right. So from this, you can directly notice the diamond little pattern you get. But you can also, if you squint your eyes, you can see these little grid lines, which is like these clear horizontals and verticals based on the center point, which is where you start. And so if I go ahead and just do a couple steps, you can see basically green is like one parity and red is the other parity. Doesn't matter too much, but we end up starting kind of like spreading out in this middle. So if you go through and just render a couple points, yada yada, you like see, okay, it's making a little nice thing. Once I get to 65, this is the first point where I basically hit the edge of my grid. And then if I look here, oh, it actually ends up making a really nice diamond. That's a cool little coincidence. All right, what happens if I try 131, which is the size of my like entire kind of grid, like one individual grid? Oh, look, another nice little diamond. And another cool property is because we have clear horizontals, this ends up hitting the exact center point, the start point, of this second diamond. Then if I do another 65, oh look, now this little side diamond is filled up. So for example, like this diamond is filled up completely. And then so forth with all of these. And I have now 9 diamonds that are filled in. And then if I go ahead, another 65, half is filled, another 131 from that point, and now it's a little bit harder to see, but if I zoom in, maybe it's a little bit clearer, maybe squint your eyes, but here you can see we have more diamonds filled in. We have a diamond here, diamond here, diamond here. I might have messed this up, something like that. It's kind of hard to see, but more or less the point is, I think here, yeah, diamond, 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 so forth. And oh, if you start looking at this, you start noticing a pattern where, hey, when I look at step 65, which is basically all it takes to fill up one full diamond, then after that, after another 131 steps, which is how much time it takes for this to basically propagate one full diamond out, we should see it fill out this kind of 3 by 3 grid of diamonds. And then, after another 131 steps, I should expect to see it fill up this set of diamonds. And if you start looking at this a little bit more, I'll explain kind of why it's quadratic. But just like tilt your head, and you'll kind of notice that, like, oh, look, it's filling out these kind of things in a nice little pattern. And so from that, another reason why it's kind of filling out exactly kind of like this is notice that we have these little grid lines, and this ends up giving us a nice little sense of symmetry. And then after, basically the time it takes from this grid, the amount of steps it takes for me to reach this outer edge is guaranteed 131 at least, my size. Because or not at least, I think always. Because basically I have to move down one square like this, one square like this, one square like this, one square like this, all the way down this horizontal to get to here. And I could also do something like this, this. I could do something like this, this. But the whole point is, notice I'm doing half my length, half my length, half my length, all this, and so it's two halves. And then for these points, the horizontals are all clear, so I can just sketch straight shot here. So after 131 steps, basically we end up filling out one new layer of this grid. So that's kind of why we get the 65 to fill out the first grid, plus 131 for every other grid. Now to see why it's a quadratic pattern. Because it's like, if you kind of see like all the people solving it, use like something like a quadratic solver, like fit it to a polynomial, and it didn't really make sense to me when I first thought about it. But now, if you treat it like a horizontal grid like this, you can, or tilted grid, I mean, you can see basically we have one square here. And then when we fill this up to this, we end up with a total of 9 squares. And when we fill this up, we end up with 25 squares if we count each of these as a square. And if you see the pattern of 1, 9, 25, I'm just gonna, to make it a little bit more obvious, what happens if I put these numbers here? You can see basically we're skipping over every other like squared numbers, like x squared. And to see like those, where those numbers would come in, if I only drew it like this would be 1, this would be 4, this would be 9, this would be 16, this would be 25, so forth. But we're not doing that, so we end up skipping basically 2 layers every time. But this is why we're getting some quadratic kind of thing. And so from that, if I can see, okay, so how many squares are there when I solve just one layer? And then I can see how many there are when I solve this many layers, and I see how many there are when I solve this many layers, I can then just fit this to a quadratic formula. And that's what we end up doing, at least in my code. We basically store like how many additional rings we have, and we store the value of it. And then eventually we just enter into this polynomial the value we get. But yeah, hopefully this gives a little bit more intuition behind it. I think don't be discouraged if you can't really just see this question and be like, oh, this is what I have to do. I think a lot of the people solving it, if you look, are people that are like very experienced. They've done like all these things. They're very like kind of competent with the stuff, and they've seen a lot of these patterns before. So don't beat yourself up. This isn't necessarily a question that you could just solve without the intuitions and assumptions you have to make from your input. So yeah, hopefully this is a little bit like sheds a little bit more light on it. But yeah, let me know if you have any questions and I'll try to solve them.